Hello, and welcome to today's presentation on descriptive statistics. As always, before we get started, please make sure that you have printed in front of you the PowerPoint lecture notes so that you can make notes to yourself as we're going along. It may also help you to be in front of a computer so that you can stop the video and do some Excel exercises with us, or maybe even SPSS exercises with us. Today, we're going to be talking about a variety of topics that are going to focus on the issue of descriptive statistics with a special emphasis on central tendency and dispersion. Then we'll see how we might talk about those two concepts graphically, and then we'll get a little bit of practice using Excel and SPSS, our primary software packages for this semester. What I might mention is that, as you can imagine, the screen will be a fair distance from the video camera, so you might have trouble seeing particular numbers. This is why it's important that we do these exercises also in class, but at least I can give you an overview. Even if you can't see all the details, I'll try to be calling them out verbally in case you're practicing on your computers while you're listening to this video. So let's jump right in and talk a little bit about central tendency. And to put this into context, you'll recall that we always want to understand where we are in the research cycle. We have these four different quadrants in our research cycle, starting out with some real-world phenomena, and we abstract from that by using operational definitions and by using sampling to get to a more manageable research representation. And then we might use any of three broad methodological categories, including experimentation, observation, or survey methods. Once we have the data resulting from those methods, we might engage in some analysis, and that's where we are today. We'll be talking about descriptive statistics. So we're landing in this portion of our very large research cycle, and we hope that this data analysis will produce some kinds of conclusions that will be relevant or generalizable back to the real world. Okay, so as we mentioned in a prior video, we have two broad classes of statistics. One is called inferential statistics and one is called descriptive statistics, and we'll be focusing on descriptive statistics. Just to remind you about the distinction, inferential statistics are used to infer or draw a conclusion about whether populations, maybe two different populations, are significantly different from each other. And this is the issue of using p-values or probability values, like you might recall from Intro to Psychology. 0.05 is an important probability in almost all of the sciences. And we're using those kinds of probabilities to draw some inferences and make some conclusions about whether two samples, or rather two populations, are statistically different from each other. By contrast, today we're going to be talking about descriptive statistics. And here we're simply using these numbers to describe or depict, if you don't like to use the circular word or have a circular use of the word describe. We will depict the data in a study. We'll focus on three descriptive measures for central tendency first. And these are things that you probably already know. You're familiar with mode, median, and mean, but just to review those a little bit, the crudest measure of central tendency is the mode, and this is the most frequently occurring score. So here we have some examples of the modal number of eyes for our species. That would be 2. Not everybody has 2 eyes, but most of us have 2 eyes. So we can say that for our species, the modal number of eyes would be 2. The modal number of fingers per hand is 5. Again, not everybody has 5, but most people have 5. That's the most frequently observed value for number of fingers on a hand. And so that's going to be our modal tendency. The modal number of years to graduate at Denison University is 4, but there are some folks who finish in 3.5 years. There are some folks who choose to find a major a little bit later in their sequence, and they stay on for a 5th year. But most people are going to be finishing in 4 years. So these are modal tendencies, and you might come up with some other examples. In fact, it might be a good test question to ask you to generate your own novel examples of modal tendencies that are different from these examples that we have here. We can also talk about frequency distributions as they pertain to modes. And a frequency distribution can have one mode or more than one mode. Maybe it has 2 modes, it's said to be bimodal, or it can be even multimodal. So I'm going to pause just for a moment and describe what we mean by frequency distributions. In a frequency distribution, we have a graphical plot of some variable of interest. And that variable is typically shown on the x-axis, which we'll see in just a moment is called the abscissa. And then on the y-axis, which we'll see in a moment, is called the ordinate, we have typically a frequency representation. Sometimes we call that a proportion that goes from 0 to 1, or if we're using raw numbers, just how frequently do we have observations across the various levels of this particular variable. Okay? And so we have a frequency on this axis, the variable here, and we might get something like a bell-shaped curve. The center of that curve would be the mode, obviously. And we might say that if we do have a bell-shaped curve, we have a unimodal distribution. So our frequency distribution has only one most commonly occurring score, but there are different kinds of data sets that might not fit that pattern. Some might have two modes, some might have several modes. Okay? It could be multimodal, it could be bimodal, and so forth. So this is the mode, the crudest of the measures. The next most refined measure is median, still an indicator of central tendency, and you can think of the word median as being a dividing line. Just like that big cement barrier on a highway divides maybe the northbound sides and the southbound sides, cuts the highway in half, maybe from north to south by having that cement barrier. We can think of the median as a barrier also between the lower half of a data set and the upper half of a data set. We can think of it as the middle score. For those of you who know something about centiles, this would be the 50th percentile, the point at which half of the scores are greater and half are less. So again, a dividing point, a median. The median is equal to the middle value when the data set contains an odd number of items. So here we have a sample data set. It's a very small sample, and it has 1, 2, 3, 4, 5, 6, 7 items in it. 7 is an odd number. So if we're trying to find the median, all we have to do is go to the center of the data set, and the center of this data set happens to contain the number 6, which is the 1, 2, 3, 4th item of the 7 in this set. So if we have odd numbers, we go to the center of the set of numbers, and we typically list them from the minimum score to the maximum score before doing this. Okay, then we might also look at the case of determining the median when we have an even number of scores in our set, and that's shown here by example. In this particular case, we have 1, 2, 3, 4, 5, 6 items, and so we might say that the centralmost items are the third and fourth items. In this particular data set, you might be able to see on your PowerPoint slide that we have the value of 5 and 7 as the centralmost items in the 6-item data set, and 6 is an even number. So the rule is going to be this. We have to take the average of the two middle values, and those happen to be 5 and 7. Their average works out to 6. So in these two cases, we happen to have a median value of 6, but we got there through slightly different algorithms, so to speak. We have one algorithm for the odd-numbered case. That's going to be the central value. For the even-number case, we take the two central most values and simply average them. Okay, the median is best when we have different kinds of distributions that might be skewed. They're not symmetrical around their midpoint. They're skewed to the left, or they might be skewed to the right. And I can give you some examples of skewed distributions, and you might want to think of some of your own examples as well. In fact, that would be a good exercise for you, because a test question might be generate novel examples of skewed distributions. But just to get the ball rolling, why don't I offer you this? You can imagine that if we have frequency plotted on this axis, and we have some variables on, or at least one variable at a time on this axis, we can say that we can look at something like income, and we can ask how income might be distributed in a frequency distribution. And you might imagine that we have lots of folks who are poor-ish, and then a few more are somewhat wealthy, and very few people over here are going to be extremely wealthy. So we would have a skew in our income distribution. Income distributions typically, in most societies, are very strongly skewed. They're not perfectly symmetric around the midpoint. They don't fit a bell curve model very well. Another one, very relevant to psychology, would be a reaction time distribution. So when we think about reaction times, we can harken back to our time in Intro to Psychology, when you might have been engaged in any number of cognitive tasks, and you were asked maybe to solve problems, and they were measuring your performance in seconds or maybe milliseconds. Okay? Frequently, reaction time distributions have a long tail out to one side, and those are going to be skewed because they're not symmetric around the midpoint. Okay? So we can have income distributions, and we can have reaction time distributions as distributions that exemplify skewed data sets. And when you do have these skews, probably the best measure of central tendency is going to be the median, because the mean can be thrown off quite a bit by just a couple of outlying scores on this side or a few extremes on this side. Okay? If you have those extreme scores on either side, it can be helpful to disregard those by using the median. Okay? All right, so you're also very familiar with this last measure of central tendency, and this is the mean. Arithmetically, we're just taking the average. You know all about that. This is the most commonly used one. I want to introduce just a little bit of terminology here, because the mean is going to be very important for many of the statistics that we do descriptively and inferentially throughout the semester. So here's some of the terminology. We're introducing a new word called mu, and that's actually referring to this symbol, which is the Greek letter for m, mu, and we can think of mu as corresponding to a population's mean. Now when we're talking about a population, we're talking about every member in a group. And as we said at the outset of this video, sometimes we have information about every member of a group, but that's fairly rare. More frequently, we have information only about a sample. Okay? So when we're talking about populations in our field of research methods, we typically use a very specific word called parameters to describe the population. And we can describe the population with respect to its mean and standard deviation, as you'll see in just a little while. When we're talking about the population mean, we use the Greek letter mu, and when we're talking about a sample that we might have, just a subset of that overall group, then we simply use the English letter m. Okay? So you're very familiar with this, and m is for mean. This is Greek for m, and so that would be the population parameter. This would be a statistic for the sample. So we have population parameters, sample statistics. Okay? And we would use this m to signify that. Sometimes we also use an x with a bar over it, and we pronounce that x bar. So a little bit of terminology here for a very familiar concept to you. You know what a mean is, you just might be a little less familiar with how we signify those. mu for the population, m or x bar for a sample. And here's the computation that you probably learned even in 5th grade or 4th grade. We can take the sum of all of our observations, x, and divide by the number of items that we have in our list, and this gives us the average. Okay? All right, so inside of Excel, we're going to learn just a little bit of syntax for making these computations. In this case, we're looking at the syntax for the 3 different measures of central tendency. And whenever we want to get a computation started inside of Excel, we always have to put in an equal sign. Okay? So you would put in equals, the word mode, you'd put in a left parenthesis, and then you'd cursor over the range of scores in Excel for which you wanted the mode. Maybe you have all of your values on a particular variable listed in one column inside of Excel. So you would highlight over that column and then close that off with the right parenthesis. So it might be, for example, you're taking the information from cells A1 through A9, and you would get the mode this way, the median this way, equals median, left parenthesis, highlight over that range of scores in Excel, right parenthesis, and you'd get the median. Just a word of warning, you might have thought that Excel would have used equals mean to obtain the mean. It's actually the word equals average. If you put in equals mean, Excel will give you an error. So just a little heads up about that. Here we want to put in equals average, and we'll use the same range of scores, and we'll pull out the arithmetic mean by using this particular syntax. Okay? So if you'd like, you can stop the video at this point and make any notes or questions that you might have about central tendency. Welcome back. We'll be talking now about the other component to descriptive statistics, and that is dispersion. And when we're describing a data set, and we're depicting a data set, and we're generating descriptive statistics, we want to know how the scores are not only tending centrally, that is, not only what the mode, median, and mean might be, we want to know how the scores are spread out. So we're talking about the dispersion of the scores, or how they are spread or dispersed around some measure of central tendency. And there are several different measures of dispersion that we can describe. In today's video, we're only going to be talking about 2 that we see somewhat frequently, and then we'll build on these as we move throughout the semester. But we'll introduce them here today first. We'll consider one as the range and the other one as the standard deviation. You may have used both of these in Intro to Psych. You probably used both of them, as a matter of fact. Okay? The range is a relatively crude measure, and it's computed very simply. It only requires some subtraction. We look at the set of scores. We might list them from lowest to highest, and we might say that the range is equal to the maximum score minus the minimum score. So in this very simple data set that I have here, that contains items of 2, 4, 5, 9, I have a maximum of 9, a minimum of 2. So my range would be the difference between those two. Max minus min, 9 minus 2 is equal to 7 units. We have a 7-unit range in this particular data set. Sometimes people express the range that way. Or what you might just do is say the minimum score was 2, the maximum score was 9. You might report the max and the min. In fact, Excel has such syntax available to you. You can put an equals max or equals min, highlight over your range of scores, and Excel will extract for you the maximum and minimum scores. If you only have 4 items, you probably wouldn't need help from Excel because it's that easy to see. But you can imagine more complicated data sets that might have thousands or tens of thousands or millions of items in it. It would be helpful to highlight over all of those in one fell swoop and then have Excel extract the highest number with equals max or the minimum number with equals min. Okay? So sometimes we're going to be reporting the subtractive value, which is going to be the range, max minus min. Sometimes we report the max and min scores. Let's get to the more complicated measure of dispersion, and this is the standard deviation, which is the most commonly used item that you'll see probably in most reports, and it's the counterpart to the mean. Frequently we report the mean and the standard deviation to give some direct indicator of a typical score. In fact, that might be a really good test question. I might give you a data set and say, describe a typical score. Notice the relationship between the word describe and the descriptive statistics that we're talking about today. And a good way to describe most data sets, particularly ones that fit at least approximately well to a bell-shaped curve, is to give a mean and a standard deviation. So here's a potential pop quiz question. What information does the standard deviation provide in your own words? Don't give us any equations, just intuitively and in English, what does the standard deviation provide? We'll let you stop the video and jot that down. Okay, welcome back. And so now we'll move on and we'll talk a little bit about computing the standard deviation. We need to come up with some quantities that you might be a little less familiar with. It's unlikely that you computed these directly and manually in Intro to Psych. During our in-class sessions, we'll be doing these in Excel, but right now we'll just give you an overview of these new quantities that go into computing the standard deviation. One of them is called the sums of squares. And the sums of squares is abbreviated by SS, and you're going to be seeing this SS designation for the rest of the semester. So let's take our first look at what this is. Okay? So to compute the standard deviation, we have to go step by step, and the first step is to get the deviation of each score from the mean. Okay? So here we have a list of scores that we might have obtained in an observational study or maybe an experiment or maybe a survey. We can take the mean, and it turns out that in this particular case, the mean of these scores is 8. Okay, so what we're going to do is first obtain the deviations. And deviations are very simple to obtain. We take a given score, which has a value of 8 in this particular case, and we subtract the mean, which also happens to be 8 in this case. So we do 8 minus 8 and we get a deviation of 0. If we do 11 minus 8, we get a deviation of positive 3. If we do 6 minus 8, we get a deviation of negative 2, and so on down the line. Okay, we get our original scores, and then we find the deviates, as we call them, or the deviations from the mean. Okay? Then what we're going to do is we're going to square the deviations and sum them to get to the sums of squares. And let's see if we can show you that on this table. Here again were the original scores. Here we have the deviations from the mean, and we had deviations, for example, that were 0, 3, and negative 2. We'll square each of those deviations in turn. So 0 squared is going to be 0. Our deviation of 3 squared is going to be 9. Our deviation of negative 2, as you will recall, is positive 4. So an interesting feature about this squaring routine is that we generate non-negative numbers. We can generate zeros, and most of the time we'll be generating positive numbers, but we can never generate a negative number because we're working within the so-called real number system in almost all of psychology. There is another number system called the complex number system that some of you might remember from trigonometry or from calculus, and that has so-called imaginary numbers whose squares can be negative, but for our purposes we almost always are working inside of the real number system, and when we're squaring we get non-negative numbers. So here's our list of numbers, and they're all squares, and then we wind up summing those squared deviates. So from the top, these are the scores, these are the deviates, these are the squared deviates, and then finally, these are the sum of these square deviates, the SS values. So to get our way all the way back to the standard deviation, we have to go through this step of finding the sums of squares. The SS is the sum of the squared deviations from the mean. In this case, it happens to be 44. Okay? A couple of different formulas that we can use to express this new quantity that we're learning about, the sums of squares, as we're talking about dispersion, and we're making our way toward the standard deviation. These are definitional formulas and computational formulas, often in statistics, we have both of these formulas available to us. I would like you to memorize this one. The sums of squares will be equal to the summation, and that's what this sigma sign is referring to, of this quantity, x minus mu, that's the population mean, so a score minus the mean quantity squared, and we'll do that for each score in our list, and then we sum all of those up and we get the SS. We can do something that's algebraically equivalent. We can take these steps, but I won't ask you to memorize that. I just point it out here so that you know that for any one of these formulas, there's really more than one way to come to the same value. Okay? So our next step in our quest to get to the standard deviation is to do something with that sums of squares and create a brand new term called the variance. Now you've heard variance in everyday life, but we define it here to be something really quite particular. Okay? So we need to get to the variance, and that's defined as the average squared deviation from the mean. So the variance itself is kind of like a mean because we're taking an average of all those squared deviations that we had on the right-hand side of our table just a moment ago. Okay? So we can compute the variance of either a population, every member of a group, or of a sample, just a subset of the group. And what you'll see in the next couple of slides is we have slightly different formulas for the population variance versus the sample variance. They're similar, but they're just ever so slightly different, and let's see if we can explain why. Here we'll take the population case, where we're going to pretend that our data set comprises every member of the group of interest. Okay? And we're going to be invoking now a brand new Greek letter. We learned mu just a moment ago for our measure of central tendency, specifically the mean. When we're dealing with population parameters, we always use a Greek symbol, and in this case it's sigma shown here. Okay? And sigma is going to be the standard deviation. We're going to square that to get to the variance, but for right now we'll call it sigma, and we're going to be using SS divided by n, where n is the number of observations that we have. And if we have one observation for every member of the group of interest, then we have population level data, and we have this as our population variance, SS divided by n. So one more time, the variance, it's kind of like a mean, but it's a mean in these squared units rather than in the original units of measure. We can go over here and we can talk about a similar formula, but now for a sample rather than for a population. So that's a distinction we'd like you to pick up on. And here we have a subset of the group of interest, and this might be more practical. We might be working with a research representation, harkening back to our research diagram, our research cycle diagram. Here's our sample, and we're still going to have the same SS as always, but now we divide by n minus 1, where n is the number of items that we have minus 1. Okay? So the only difference is whether we divide by n for the population or n minus 1 for the sample. We'll let you think about this just for a moment. Assuming SS is constant, which formula will generate a larger variance? We'll let you stop the video and think about that. Okay, we'll welcome you back, and this time I will help you out with an answer, because this might be a little bit subtle for some folks. And the idea is that all other things being equal, the sample's variance will be larger than the population's because of this, n minus 1. When we are dividing by a smaller number, we are going to wind up with a larger outcome. So we have a relatively small denominator that generates relatively larger values. Conceptually, we might ask, why are we doing that? Why are we dividing by n minus 1? And the answer is a little bit subtle, but let's see if we can give you an appreciation for it. If you can imagine that you have a bell-shaped distribution of scores in your sample or in your population, if you're doing your sampling, you're probably not going to be getting the most extreme scores in your sample. Every once in a while you'll get the most extreme scores, but in most samples you will not get the most extreme scores. So if we really want to capture the full variability by using something like the standard deviation, then we'd have to somehow capture those most extreme scores, and we probably don't in a sample. So how do we compensate for the fact that we didn't capture the most extreme scores? What we do is we manipulate the denominator by making it just a little bit smaller, and when we divide by a smaller number, we wind up with a larger value, and this is a way of numerically compensating for the fact that we didn't quite grab all the most extreme scores. We don't have to do that in the case of the population because we have all the scores definitionally, but in a sample we almost certainly don't have all the scores, so we try to compensate by doing this. And researchers can show that this is actually a fairly conservative estimate of the full spread, and what we mean by conservative in this case is we might actually be overestimating the dispersion of the data set, and that's actually a good thing to do as we'll see when the semester progresses. Okay? All right, so let's move on. And now we'll say finally, to get from these squared units that we've been dealing with the sums of squares and the variances, back to the regular units, or the original units, we need to take the square root of the variance. So I'll read this first to you. The standard deviation is the square root of the variance, and we're going to make that today's main mantra. So I'll ask you to say it with me. Okay? Everybody, say it together. The standard deviation is the square root of the variance. And we will say that mantra several times this semester. It's a very critical mantra for our purposes. And this is true whether we're talking about a standard deviation of a population or of a sample. So now what we're going to do is show you the same slide that we had a moment ago, but we're taking the square root, and now we're dealing with standard deviations as opposed to variances. So we have the population standard deviation, the sample standard deviation. Okay? The standard deviation is the square root of the variance. Okay? We can express this a slightly different way. This might look like a little bit more daunting type of expression that we have here. This is really the same expression that we had a moment ago, but what we've done is we've taken the sums of squares and we've unpacked it. You remember a moment ago we defined the sum of squares this way, and we're doing that here, substituting out the SS as you see here and here, and if we keep our eye right on that one, we can unpack that SS and turn it into this expression, and now we have a way of computing the standard deviation using this kind of a formula. Okay? So this is another way of saying the same thing. Okay, that was a lot. We've gone through a lot of ideas there, and we could say that we want to review these concepts. We focused on two measures of dispersion. In our topic of descriptive statistics, we mentioned three different kinds of measures of central tendency. We now talked about two types of dispersion, and these are the range and the standard deviation. The range was very simple. It was the max minus the min. The standard deviation was indicating approximately how far on average scores depart from the mean. So that would have been a good answer to your pop quiz question. Okay. The standard deviation depends on some important quantities that we had to introduce. These were the SS and the variance. Okay, so we're just reviewing those ideas. And the formula for the population variance is based on n, and it's slightly different from that for a sample, which is based on n minus 1, for reasons that we described earlier. And our main conclusion from all of this was our mantra, which was that the standard deviation is the square root of the variance. Okay. So what I would encourage you to do now is stop the video and see if there are any questions that you have as you're looking over the earlier PowerPoint slides, and jot down your questions. Also, you might jot down what was particularly clear but new to you and something that you think you learned from this, and we'll take your responses in class. Okay, welcome back, and we'll talk now a little bit about graphing. Now, this is important also when we're describing our data sets and we're engaged in descriptive statistics. We sometimes will write in English what the mean and the standard deviation had been, but sometimes we want to show this information graphically. So we're going to learn some of the graphing tricks that make for really good practices in any kind of a science, including psychological science. So some of the terminology that I'd like you to become familiar with would be terminology that refer to the two axes usually shown on a graph. As I've mentioned earlier, the x or horizontal axis is called the abscissa, and that does have a C in it. Although it isn't pronounced, it's a silent C. It's the abscissa on the x-axis. The y-axis also has a fancy name. It's called the ordinate, as we alluded to earlier. By convention, you might remember which variable, the IV versus the dV, goes on which axis. Okay, we'll let you think about that just for a moment, and I'll give you that response right now. The x-axis or abscissa typically contains the independent variable, and then the y-axis or ordinate typically contains the dependent variable. Okay? So that's a convention in almost all sciences. Occasionally, we get away from that. If we're doing frequency distributions, we have a fixed y-axis, which is always frequency, or if you prefer to explain it proportionally, we have 0 to 1 for the proportions there, and then the one variable of interest will go on the x-axis. But if we have two variables, an IV and a dV, by convention, we plot the IV on the x-axis and the dV on the y-axis. And we have a script for describing that. So in your professional lives, after you've graduated from college, there's a good chance that you're going to be presenting some kind of quantitative information, and your audience will be relying on you to reason with them quantitatively. And when you're showing the graphical information, it's good to begin with a script that I will share with you now. The script goes like this. We typically state, and here we go, in this graph, comma, dV is plotted as a function of IV. Okay? In this graph, dv is plotted as a function of iv. So we'll see a few examples of that. From my own laboratory, we have a graph here, and I can apply the script that I just shared with you in the following way. In this graph, motion sensitivity is plotted as a function of Q condition. Okay? Now we can unpack that a little bit further, and we can say in this graph, motion sensitivity, as indicated by d prime, is plotted as a function of Q condition. Okay? So we can describe this graph this way, and when you're reporting in this course and in future courses and in your professional lives about different graphs, we encourage you to use that script. Okay? We might ask, how many levels does the IV have and what are they? In this particular case, the IV, which is plotted on the abscissa, has 3 levels, and they are valid Q, no Q, and invalid Q. What's nice about having a script in our back pocket, so to speak, for describing graphs is sometimes we might not even know what the variables are, we might not understand them, and yet we can still begin to describe the graph by saying that dv is plotted as a function of iv. So as a naive viewer of this video, you might not know what valid Q, no Q, and invalid Q are, but you still have a script for talking about this. Okay? So we have one independent variable, and it happens to have 3 levels, and harkening back to our earlier sections in this video, we might plot each of these values within each of the levels of our Q conditions up to their mean, plus or minus some standard deviation. We call these error bars, and these can refer to the range, they can refer to the standard deviation, or other indicators of dispersion, but really good graphs typically have some indication of central tendency and some indication of dispersion. Okay? All right, sometimes an experiment has more than one IV, and that makes things a little bit more complicated. In fact, researchers call experiments or studies that have more than one independent variable complex designs, or sometimes factorial designs. So we can use that new word, factorial design or a factorial experiment, whenever we have more than one independent variable. Now that creates a complication when we're graphing, because we still have one dependent variable, and now we have more than one variable to be plotting on our x-axis, but we only have one x-axis. So the idea is typically this. We typically plot one of the IVs on the abscissa, and the other IV by using different symbols in the legend. And we call these different colors in the legend, or different dashes in the legend. We call these parameters. So just for clarity, we've used the word parameter twice in this video in 2 slightly different ways. First, we introduced parameters in contrast to statistics. Parameters like mu and sigma describe a population. Statistics like x bar or lowercase m or s describe the sample, okay, the mean and standard deviation of a sample. Here we're using parameters to refer to the different colors in our legend whenever we have more than one independent variable. And here's our variation on the script. In this graph, dv is plotted as a function of iv number 1 with iv number 2 as parameters. Okay? So in this graph, and we have another one here from my lab, in this graph, discriminability is plotted as a function of task with training as the parameter. Okay? We can say that a little bit more precisely. Discriminability, as indexed by d prime, is plotted as a function of task with training as the parameter. And we might ask, how many IVs do we have here? Well, here's one on the x-axis, and it happens to have 3 levels, and these are direction, speed, and luminance. So we have 3 levels of our task variable. And for our parameterized variable, that's the second IV, which we are showing by parameter, or by different colors or different symbols, well, we have 2 levels of our direction training variable before versus after direction training. So even if we don't know what these mean, we now have a script for describing relatively complicated graphs. Okay? We would also say that this is a 3x2 design, or equivalently a 2x3 design. And those are referring to the fact that we have 3 levels of one variable and 2 of the other, and there is no particular convention for describing this axis first or the parameterized variable first. You can do them in any order. This is a 3x2 or equivalently a 2x3. Here's another example of a 3x2 or a 2x3, and as always we're plotting up to something like a mean, and we're giving something like a standard deviation by error bars. We'll practice one more time using our nomenclature and our script. In this graph, mean duration of eye contact is plotted as a function of gender pairing, with conversant as the parameter. This also is a 3x2 design. We have 3 levels of the gender pairing variable, and we have 2 levels of the conversant variable. Okay? Now what's interesting about graphs is that graphs usually convey quite readily to your audience what's going on in your data set. It's a very nice way of describing the data set, and that's what we're doing in our descriptive statistics. There's another way of showing the same data, and you can do it in tabular form or table form. And here is the same data set shown now just by way of table. Most people find this a little bit easier to interpret graphically than that. And that should be a clue to you that whenever possible you might want to graph your data rather than putting them in table format, but sometimes for various reasons tables will be required by a journal or required by a peer reviewer, whatever the case might be. So we can present the same information graphically or in this tabular manner. Okay, another important feature about graphs is that the graphs should always start at 0 if we want to retain some kind of proportionality in the data that we're showing. And you might harken back to our earlier conversations on ratio scales versus interval scales on this point. So it's really important that we have in the lower left-hand corner of our graph where the ordinate is starting, we start out with a 0, at least in most cases. If not, the graph will lose proportionality and become a little bit misleading. Small differences could appear huge. So to appreciate this point, this graph on the left retains proportionality. It has a 0 in the left-hand corner. We're going to plot exactly the same data over here on the right, but we're now going to replot not with a 0 starting point, but maybe by starting right about here as the introductory point for our ordinate. Okay? And this is now going to be disproportional. So in this graph, we're plotting mean height as a function of gender with male and female levels shown this way. And you can see that here we have what is probably a good visual depiction of the actual difference in heights between males and females on average. The average man, if he is that tall, then the average woman might be about that tall. They're fairly similar, but you might notice that he is a bit taller. Okay? What's misleading about this graph is that it now takes exactly the same data, a mean height of 68 inches for men, 64 inches for women, but it looks graphically as if he is twice as tall as she. But in the real world, men are not twice as tall as women, and yet it looks that way here on this graph. So this graph can be very misleading, and it's misleading because we've taken away the 0. We now no longer have proportionality. We've moved out of the ratios that we would like to maintain graphically. So whenever possible, please keep a 0 here. Okay? This is the graph that's messed up. All right. Okay, we'll move on now, and we'll talk just a little bit about getting some Excel practice using the SD, or the standard deviation. Okay, so let me hop out of this. Okay. And we're going to pretend here that we've got a data set inside of Excel. And in Excel, we're going to look for some descriptive statistics on our data set. We're going to be looking for a mean and a standard deviation. Okay? So here's our mean, here's our standard deviation. And what we'll do is take advantage of some of the syntax that we used earlier. So we're going to pretend that we have a list of scores and 20 of them. I realize this is very small and difficult for you to see. And we've used the Beck depression inventory on this particular sample to find out how depressed these patients might be. And we're getting scores from the Beck depression inventory here. We have a list of 20 scores. We might want to get their average. So you can instruct me, pretend like you're talking to me live. What would the syntax be if I wanted to get the average here? Okay. I would use equals average. You might recall that I open a left paren. I highlight over the range of numbers for which I want an average. I put in a right paren and I hit enter. And in this particular case, I get something like 5.45 as my average. Okay. I can also get the standard deviation. And to do that, I need to introduce some new syntax. And I'll call this out to you. In fact, I'll show it to you here. Let me take this down just for a moment. Okay. We're going to learn a new Excel function. And just to remind you about what a function is generally in mathematics, as you see here, a function is a rule for turning one number into another number. Okay. We can use something like a linear function that you might remember from 7th grade or so, where you have y equals mx plus b. Okay. And here we're taking an x value and we're converting it into a y value by multiplying it by some slope and adding some kind of intercept to it. And that might be positive or negative, either for the slope or for the intercept. So this is a rule for turning one number into another number. In Excel, we can turn one number into another number using different kinds of syntax, using different kinds of functions. And one function that we just used was the average function. We also have the standard deviation function, which is abbreviated equals STDEV, left paren, we highlight over the range of numbers for which we want to score, right paren, and away we go. So let's bring that all back. And we'll go back to our Beck depression inventory numbers, and we had a mean across these 20 numbers of 5.45. I'll now use that syntax. I'll put an equals STDEV, left parenthesis, so that's an abbreviation for standard deviation, STDEV. As before, I highlight over the range of scores for which I want the standard deviation. I put in a right parenthesis, and I come up with something like 1.932 as my standard deviation. So I now have some descriptive statistics of this particular data set of depression scores, and they have a mean of 5.45 plus or minus 1.932, the deviation on average, the average extent to which a score departs from its mean. Okay? So that's our little introduction. And again, I apologize for the small print there. We'll do this live in class, and I think you'll see it all quite clearly. Okay. So going back over to PowerPoint, we're now up to our next section, which is the section on SPSS. And using existing files inside of SPSS, we might open some data files when we're in SPSS, and when we do, we're going to be looking for a particular extension. And that extension will end with .sav. That will be an indicator that we have a data file inside of SPSS. And inside of SPSS, you'll see that we have two different views. One is called variable view, and one is called data view. SPSS is a little bit similar to Excel in that they're both spreadsheet-based. But inside of SPSS, we have these two different views. And in variable view, what we're going to do is have different rows that are going to correspond to the variables that we might have. So in our prior example, we might have differently numbered participants, participants 1 through 20. And then we have a score for each of those participants. And we'll have their Beck depression inventory score as another variable. So we have the participant number, and then we have the participant score. Those would be two variables that we would begin defining in variable view in SPSS. Then we click over to another tab, and we have data view, and now each row corresponds to a different participant called a case in SPSS. So the cases can be individual people, each in different rows. If you're working with rats, they're individual rats in different rows. If you're working with school districts, and you have school district A versus B versus C versus D, that becomes your set of cases. So whatever the unit of analysis you might have, each case within that unit of analysis is going to be shown in different rows in data view. Note that variables are in rows in variable view, but in columns in data view. So there's a 90-degree rotation that we'll show you in just a moment. Okay, let's see if we can get some practice entering data in SPSS. And we're going to start out by going into variable view. And we'll always begin in variable view. And each variable is, again, in its separate row. And here's a good habit. We might always make the very first variable some kind of participant identification variable. So we can say that the first participant is P1, the second participant is P2. We would call that variable participant ID. Okay? And typically, we have two ways of defining a variable, either as being numeric or as being a string. In Excel and in SPSS, almost all of our variables are numeric. This is a quantitative reasoning course, after all. But every once in a while, it helps us to describe a variable qualitatively by typing in words to describe that variable. And when we're doing that, and we have these kinds of variables for which we want to put in actual letters rather than numbers, we have to define the variable as a string. Okay? So we'll click on the string option there, and then on the far right-hand side of our variable view, we get to specify whether we have a nominal scale, a ordinal scale, or as SPSS calls it, a scale scale, which is to say interval or ratio. SPSS puts the two of those together. Okay, so we'll take an example here, and then we'll go out to SPSS. Let's say that we want to define a data set that has participant ID, and maybe we have a bunch of participants who vary from each other in their religious affiliation. So we want to make the religion a variable. So we have the participant ID, and now we have a religion variable. And we might define the religion variables along these dimensions. We might have people who identify as Buddhist, Hindu, Islamic, Jewish, or Christian. So in variable view, what we might do is go to a values section and put in 1 correspond to Buddhist and 2 will correspond to Hindu and so on down the line. We can use these value labels inside of SPSS. So let's go ahead and do that. We'll have you sign on to SPSS if you could. Okay. All right, and we're going to see in SPSS that we have this big spreadsheet. Okay. It looks a little bit like Excel, except we have variable view and data view. If we go over to variable view, you'll see that what we have is the opportunity to define our first variable, which I've defined as participant ID. Okay. So I clicked up here. I typed in participant ID all as one word. SPSS does not like spaces in any way. And I've gone over to the type, and I've clicked on that, and I've made it string because I want to be able to put in that this is P1 or P2 or P3 for participants 1, 2, and 3. Okay. That's our first variable. Our next variable is really the variable of interest in the study. We're going to define it numerically by assigning different values to different kinds of religious designations. So I'm going to go to my values section right over here, and I'm going to click on that, and I would put in a 1 and type in Buddhist, a 2 and type in Hindu. You can see that on your SPSS spreadsheet when we're in class. I realize it's a little bit small right now. Right? And all of this is the view inside of variable view. Okay? So now what we'll do is we'll click over to data view, and you can see that I had put in previously participant 1, participant 2, 3, 4, and 5. So this is my string variable. I've labeled each of my participants. And now I want to put in some value 1, 2, 3, 4, or 5 corresponding to that particular participant's religious affiliation. So I might have, for example, 2, 3, 1, 4, 5. Okay? And then I can go to view, way up top here, and I can go to value labels. Okay? And I can see that I can toggle back and forth between the label representation or the numeric representation of these. I can turn them into 1s through 5s, or I can turn them into more meaningful English words, and we can see which of our participants has which particular religious affiliation. Okay? All right, so that's our little introduction to how to get started inside of Excel and how to get started inside of SPSS. What I'd like you to do now is jot down what you found particularly clear about this presentation and what still needs some greater clarification, and we'll have that conversation in class. See you in class.